Hi, let's talk about BOM consolidation because it can be quite an important subject when you're designing your product. Now, I've done videos on schematics before, and I'll link them in down below and at the end if you haven't seen them. One is creating a nice readable schematic here, and another is what is schematic ERC. And I've done other videos on design rule checking and things like that. So designing your widget like this is a multi-step process. Typically, you'll design your schematic first, and then you'll do your electrical rules test in your ERC, then you'll lay out your PCB and you'll do your design rules check-in, and then you'll do generate the manufacturing files for it, and then you typically get it assembled and everything else. And I've done many videos on design for manufacturing, for example, but there's a step in there which I have mentioned in, off and on in a few videos, but I've never done a dedicated video on it, and it can actually be quite important. It's BOM consolidation. What's BOM consolidation? Well, let's find out. Now, BOM consolidation, whilst there are multiple parts to it and there's more aspects than just the BOM itself, it is basically done at the product schematic design stage, or after you've designed your schematic. After you design it, you'll do the electrical rules check-in, of course, but before you do that, you want to do some BOM consolidation. Now, this is actually, there's 4 aspects to this. It's not necessarily just about the BOM, but that's pretty much what we're going to get at in this video. So you can think of it more in terms of like a product parts consolidation, for example. However, we'll just call it BOM consolidation for the purposes of this video. So let's just assume that you've already designed your schematic. You've laid it out, it's beautiful, and you're about to do your ERC. But before you do that, you want to think about, this is part of the start of your design for manufacturing steps that you're going to do to can actually design and build your product. Okay, if you're just making a couple of them, it doesn't really matter. BOM consolidation is not for every project, but if you get more and more serious in your designs, and especially if you go into high volume manufacture, and especially with large or complicated boards that we're going to look at today, or even larger ones like the ones you see behind me, these motherboards and just these enormous boards like this, BOM consolidation can be really important. In fact, one of the most vital aspects of designing your board. Now, there's potentially 4 parts to this, and we'll go through them, and they're kind of intermixed, and some of them may or may not be relevant depending upon your circumstances, as we'll talk into. But the first one, after you've designed your schematic, is to consolidate your values, i.e. your parts values. And we'll get into this in detail in terms of, say, the resistors. How many different types of resistors are you using? How many different types of capacitors? Can you actually change any values on your schematic to match some other part that you're also using on the design? Now, the second part is parts consolidation. This is where you might want to reuse your parts on your schematic. You may not have thought about this as you're designing your schematic, but you should have, in terms of like, can I reuse this component somewhere else in the design? Have I got 2 different types of diodes? Can I get away with 1? Have I got 5 different types of transistors? Can I get away with 2 or 3 different types and share them, for example? And the third type of optimization, which is essentially what we're doing here, we're optimizing the design. The third type is to consolidate your footprints. And we'll go into detail why you actually might want that. Because, well, if you don't know about design for manufacturing and assembly, you could really come a gutser where it could actually cost you more money to get your device manufactured. And the fourth type of optimization is cost optimization. Can you actually substitute in parts that have lower cost and things like that? We won't really cover that in this video. What we're going to look at in this design is really, can we actually reuse component values? Can we get away with using all 10K resistors? The holy grail of electronics design, by the way, is to use 1 value of resistor and 1 value of capacitor in your entire design. It's possible. Give it a go. Anyway, so we won't be looking at cost, although we might touch on that. So anyway, let's get to the first optimization or consolidation type, which is trying to consolidate our values. Right, so I'm just going to go to the KiCad website here and just get a random project. Not necessarily random, I wanted a complex project. So I found this one, the CIAA. I've mentioned this one before. I've used this in some KiCad examples, and it's a 12-layer design. So hats off to the team that's done this. It uses a Xilinx Zinc processor, and it's hugely populated, a large number of parts, both front and back, as we'll see. And View Project takes you over to the GitHub here. I'll link this in down below. So it's a really good example. If you're looking to like hone your skills, for example, like laying out boards, for example, and you think you're getting really good, well, give this one a go. You know, like import the schematic, it's all ready to go, and then try and lay out the board yourself and see how you go. So anyway, that's bit of a tangent there, but people keep asking that. How can I get better at PCB design? How can I improve my skills, have it better on my resume and things like that? Well, it's by taking a design, an existing design like this, or fast track way, take an existing design and then start laying out the boards. Just like blank the board, start from scratch, see if you can do it, and preferably build up, make sure it works. But anyway, here's the GitHub here, and it's got the KiCad file. And anyway, it generates a bill of materials like this. This is what most CAD programs will generate. They'll generate a Excel file like this, a CSV file of all the components, you know, the number, the quantity you've got, the component reference designator, the description, and then maybe like supplier part numbers, manufacturer part numbers, and all that sort of jazz, footprints and values and all that sort of stuff. Now, we won't use the Excel one today because the KiCad has this awesome plugin of an interactive BOM. It can generate these. It doesn't come standard with KiCad. You've got to install it. But this project actually already came with this. It's a HTML file and it's interactive. So this is the BOM for this particular project here, which is like a general computing, educational computing platform, I believe it is. And this is actually great for, you can see that it highlights the components on the board here, both front and back, as well as we go down. So this is handy for like manual pick and placing and stuff like that. So this is just, so hats off to whoever wrote this plugin. It's really fantastic. But I chose this example because it's a really complicated project. If we go up here, now if we have a look at the stats for this board, it's got 225 components on the front, 344 components mounted on the backside. Most of those are probably bypass caps. 569 components total. You know, that's a huge number of parts. But of course, it's still nothing compared to like enormous motherboards and, you know, hugely other complex industrial bits of kit. But it's a really good example of a relatively, you know, complex modern board that you might want to have to get manufactured once you get serious, if you're designing, you know, serious products. And look at all the parts down here. Here they are. As we said, here it is. There's 161 different components on this thing. Why does that matter? 161. That's interesting. This is where design for manufacture comes into it. Now, of course, you have to get your little, assume this is this board, you have to get this board pick and place assembled, because you're not going to hand assemble something like this. That's just like, I've done it, and don't subject yourself to that. Anyway, you're going to get your widget. You're designing this thing for high volume manufacture. It's going to be pick and place machine assembled. Well, you've got to know all about pick and place machines, in particular what your particular assembly house has, and you should actually choose and talk to your assembly house even at the design stage, even when you're designing the schematic. If you're serious about this sort of stuff, not necessarily, you know, if you're Apple and you're designing the new iPhone, of course, yeah, that's absolutely essential to do something like that, or extremely high volume, you know, farty novelty gadget in their billions or whatever. Yeah, it can really matter, but most designs you probably don't have to talk to the manufacturer, but you should keep some basic rules of thumb involved with pick and place machines. Now let's have a look at a typical pick and place machine, shall we? Stick with me, because this actually guides a lot of our things that we're going to talk about in our BOM consolidation. So buckle up, Dorothy. Kansas is going bye-bye. So I just picked this one, Yamaha, one of, you know, the best in the business. This It's a YSM40R for those playing along at home. Ultra high speed, 200,000 CPH, which is components per hour. That's the rating that they have in here. Basically, knowing what your assembly house might typically have, and if they've only got one of these machines, then you can come a gutser on this board already, even if they have two of these machines. You can come a gutser already. Why? Because if you go down here, it actually supports. If you go down here and check out the specs down here, here it is. It's got a maximum of 80 feeders. Now, you've seen these before. These are reels that your components come on, or your resistors, capacitors, diodes, transistors, your ICs, and even your battery holders, for example, your CR2032 coin cell. They all come, everything pretty much comes on reels. You can get trays, but let's not worry about that. Now, these have to go into a feeder into the machine, and you can physically see these feeders up here, and these are cassettes that hold these reels and insert. So we've only got a maximum of these feeders, but fine print, 8mm tape width type. So this is an 8mm type one, which holds, you know, typical resistors and capacitors, and it can only hold a maximum of 80 of these in the machine, or even less if you have wider parts, like a CR2032 battery, for example. That could be like a really wide tape, and that'll tape up several slots in there. So what that means is that your assembly line that you're using at whatever manufacturer will be limited to how many of these reels they can hold. So if your design here has more than 80 parts, absolute maximum for that particular machine, then it's not that you can't get it manufactured, it's just that they'll have to put it through multiple passes. Then they'll have to either use different lines, or they'll have to have two of these machines in series. It can pass through one machine, then it can pass through another, and some big assembly houses will have multiple ones of these machines. But just remember, this can be a big limitation for your design, and they'll charge, yes, they'll manufacture the board for you, and they often won't even tell you. They'll just quote you a price, and it's going to be a much higher price to assemble your board, because they know they have to pass it through 2 or 3 times, because you're using 160 different types of components, which all have to come on their own reel. But not only that, then you have to actually go out and buy and source all of these different types of parts, and just missing one part out of those 160 parts, you might not be able to get your product manufactured, or you could get it almost all manufactured except for one part. So the more parts different types of parts you use on your design, the higher the risk, the greater the potential assembly cost, and like all sorts of issues to do with that. So reducing the different types of components is what we're talking about here in terms of BOM optimization. You want to minimize the number of different BOM items, bill of materials, by the way, I've mentioned that, haven't I? Bill of materials, different BOM items that you have, the different parts. There's huge advantages to doing that. And the bigger and more complex your boards get, the more important this becomes. So we talked about like 3 different potential ways to do this. The first one is value consolidation, which is generally you might get this for resistors and capacitors. There's other components as well, but they're the 2 biggies that you want to consolidate. Now, look at this. How many different types of capacitors do they use in this design? Let's have a look. It starts at component number 1 here. It's good that they've all sorted them by capacitors. 26 different types of capacitors. Some pick and place machines might only support 40 reels. We've already taken up half of our reels, reel space, just with capacitors. There is no way, and this is, by the way, I'm not sledging the designers of this thing at all. They just didn't bother to do BOM consolidation. There might be reasons they only wanted, 100 of these made. It didn't matter, right? Just the design cost and getting the manufacture was nothing compared to, but if you wanted to make 100,000 or 1 million of these things, you don't want to be having 26 different types of capacitors. That's just nuts. So we want to go in and do some BOM consolidation. Look, and check this out right off the bat. We've got 1 capacitor, 11 puff. 11 puff. Why? When we've got another one which is 13 puff. We've got one of those. We've got one 16 puff capacitor. We've got one 24, but two 18 puff. Come on. You can't tell me that you need precisely 11 picofarads and 13 picofarads. That is ridiculous. The capacitors are going to be 5-10% tolerance anyway. So the difference between 11 and 13 puff. Now, look, if you're doing a complex RF design or something like that, then yeah, okay, that could matter. But in a lot of cases, you're just going to choose these values because they came out of an application note, or it's what came out of your calculator, for example. You might want to, okay, I want like a 1 megahertz filter, for example. You do your calculations and it comes out to 11 picofarads or 11 nanofarads or whatever it is, and a resistor value of 6.25K. So you choose the closest E96 preferred value to that. Well, you don't really have to. So you really should, as part of this optimization process, this BOM optimization, is go back, look at your design and just think critically, like, really, do I need an 11 picofarad? Couldn't I have used a 13 or maybe a 16 or maybe even an 18 picofarads? I mean, come on. Right, so let's go into the schematic here and have a look. C92, there it is. C104, 11 picofarads and 13 picofarads. What's it used for? The power supply. Look at this. Look at this. The power supply. A switch-in power supply. That's it. 1.2 volt power supply. And they've determined that they need 11 picofarad capacitor and an 8.87K resistor. I mean, this is just silly stuff, right? There is no way you need that precision in a compensation network for just a switch-in regulator. Obviously, these values have just popped out of the confuser here, and they've just whacked them in there and said, right, we need 11 picofarad capacitor. We need a 13 picofarad capacitor. Like, give me a break. No. Go back to the data sheet here, TPS 65400. This is an exercise for those playing along at home. Go into the data sheet and actually have a look at where it'll probably give you the equations for calculating the compensation values and things like that. Is it that critical? The answer is almost certainly no. You could easily consolidate these two values here, which are the only ones used in the design. It's the only place it's used, and you've got to take up you've got to go buy a whole reel. Then your purchasing officer has to then go and purchase these from somewhere. You've got to find them in stock. They may not have them in stock. It could screw up your entire production schedule just because you decided you needed 11 picofarad cap in there. Now, this is not uncommon in the industry. It's happened to me many times, is where the purchasing officers, and yes, large corporations will have purchasing officers, their sole job is to buy all these, source and buy all these parts for the new, for the latest production run of your widget that you're trying to actually produce. And they will often come to you and say, look, I cannot for the life of me get an 11 picofarad capacitor in an 0603 footprint. The whole world's out of them. I've scoured the grey market, cannot find them. Can we have a substitute? And a good bill of materials will also have like a substitute, like different brands. In fact, it was company policy at some companies that I've worked at, you would have, especially like military type ones, where you'd have 3 different manufacturer part number variants. So you'd have 3 choices so that the purchasing people can go and choose any one of those values, and it doesn't matter, that part was fully qualified for use in the design. But often they'll come back and they'll go, look, I cannot get this. Can I buy something else? And you might have to do an engineering change request or whatever it is to go, yep, look, I authorize to use a 13 puff capacitor in there instead of 11 puff. I was just lazy when I designed it, and it doesn't matter. A rat's ass that it's 11 picofarads or 13. Now, values like these ones, for example, this obviously sets our value, our 1.2 volt voltage reference. So these values are fairly, the ratio of them is fairly critical. But you could actually put in a 10K here, like a 13.3K, okay? And yes, 13.3 here, if we go to 1.33 is all 3 columns there is an E48, E96, and E192 preferred value. So you can actually get that value, but should you actually be using this? Now, generally when I'm doing a design like this, I will typically go, look, I'm going to use a 10K as this bottom one, and then I'll calculate the top one, and then I'll figure out what, then I only need to get one oddball value up here instead of two oddball values. And here's the next thing, with value consolidation, it can actually be better and cheaper and more beneficial to use more resistors in your design than to choose the right value and have to get another complete reel and have another individual BOM item. For example, this is a classic example of it here, where you need a specific value to meet your tolerance of your 1.2 volt voltage rail here. Now, just for argument's sake, let's say that you chose a 10K resistor here, for example, and you did your calculations and found that your 1.2 volts within whatever tolerance you required, like a 4.99K, for example, or let's say it popped out at 5K, or even 4.99. What do? You don't necessarily go and just buy yet another reel just for that one value. It takes up another slot in your pick and place machine, more bill of materials items, when you can just put two 10K resistors in parallel. You've reused one of your parts here, and sure, you've put in an extra resistor, and sure, it's more board space, and sure, that might be important if you've got a real ultra dense design. You may not have the luxury of being able to put two resistors in parallel, but in probably the majority of cases in practice, you are going to have the room to put in the two 10K, or make room. A good PCB layout designer can always make room for that extra resistor, just so that you reduce that one extra BOM item. And you can do this again, 16 puff up here, 1.2, 1.5 nanofarads. Couldn't we have used 1.2 nanofarads? Look, do we have to use 11K here and 11.3K here? Really? So this is a really good example, and it's why I actually picked, when I saw this project, I just picked it like at random, a complicated one. And when I saw this, I went, good example. Lots of different parts in the BOM. So yeah, just go through, read your data sheets again, go through your calculations, reevaluate, do your engineering evaluation, and all the stuff that goes along with qualifying your design and everything else. And almost every project I've ever done, and it might be the odd exception, but a vast majority, I've been able to BOM optimize in some way when it comes to capacitor and resistor values. Then if we just quickly look at some of the memory on here, look, we've got termination resistors, 40.2 ohms. Yeah, we've got a lot of them. That's fine. This is obviously popped out of their polar impedance calculator, or whatever it is they use to calculate the transmission line impedance. We've got 80.6 ohms here, for example. Not sure what that one's doing at 240 ohms and things like that. So all of these oddball values will pop out of your confuser here, but don't necessarily blindly follow them. That can lead to a BOM like this one, which, hey, as I said, if you're making 10 or 100 of these, you just might not care. It popped out. I couldn't be bothered spending another minute. I was on a tight deadline. I needed to design this thing, and just, throw it out the door. And it's fine. The manufacturer will do it. The purchasing people will purchase them all, and Bob's your uncle. But there can be huge value in just spending like a few hours. It's not, it's like this design here. Sure, okay, I might spend a whole day like checking this. Pull up the data sheet for this. Do we really need our 10.7K in there and things like that? So yeah, you might spend a day just tidying up this, but they obviously spent months designing this thing. And well, and there's some argument over when you might do this. Some people might actually, okay, go and the number pops out of your confuser, so that's what you put in your schematic. And then, and I've done this myself, and there's valid arguments for it, is once you've done that, then generate your BOM and then go in and see if you can optimize the BOM. You can actually do it right at this schematic stage. While you're designing, oh, I'm not going to use a 6.81K so anywhere else, so I'm going to put two resistors in series or parallel to get near enough value or something like that. So you could argue that it's better to do as a separate pass, because then you're not bogging down your design process. You're getting the design down first, and then breathe in, breathe out. I finished my schematic. Okay, let's, you go get your extra coffee or whatever, chocolate or whatever it is you need to keep going, and then you go do your second pass BOM consolidation. So that's the first part, consolidating your values, mostly resistors and capacitors, but some other parts. Now the second part is parts consolidation, where well, do I really need that part, or can I reuse that part somewhere else? Not just the value, but the actual component itself. Now, I'll link it in. I've done a video on Munson and bypass capacitors visualized. Like Munson, Madman Muntz, back in the day, used to be famous for carrying around a pair of side cutters, and whenever one of his designers of one of his analog, none of this digital rubbish, analog TVs, I finished my design, they showed it to Madman Muntz, he'd come around with his side cutters and start snipping out components one by one until it stopped working. And when it did stop working, he put that last component back in and go, right, toss those parts out. We obviously didn't need them. And that's Munson. And it is actually a real thing. And one thing where it really comes in is bypass capacitors. I've shown that. I'm not going to say that are they really needed. In most cases, no. It's just general rules of thumb where if you haven't analyzed your power system, and it can be quite complex to do this, requiring real sophisticated software and specialized software to do it. Do you need all of these bypass capacitors? Do you need a 10 mic, a 1 mic, a 100N, a 10N, a 1N, all on the power pins, for example? FPGA data sheets, for example, like I'm sure, go check up the data sheet for the Zinc FPGA used in here. They've probably got an application note just dedicated to bypassing. And you can go over here to Maxim, for example. There's Xilinx and there's Altera and other FPGA manufacturer app notes on this. Power supply solutions for Xilinx FPGAs, for example, and how like you need X amount of bypassing in the impedance curves, and why you need all these different values and like power up surges and things like that. And there's all sorts of stuff involved in it. It's endless. It really is endless. Anyway, the point is, do you need all of these capacitors here? The answer is almost certainly not. So while they're all the same values. So, but still, even when if you use too many capacitors, even though you might have 4,000 on a reel, you're manufacturing a lot of boards per hour, your reels can run out earlier, and then somebody's got it, a red light flashes on top of the machine. Quick, I've got to the whole production line is stopped because you ran out of your 10 nanofarad capacitors because you used 10 gazillion of them on your machines. Somebody's got to come around and replace the reel and to start up the line again. So, and they cost money, especially like you're using the more expensive 1 mic and 10 microfarad ones, for example. They can be expensive parts, but often, you can do some months in and you can get away, but sometimes you won't know this at the design stage. You might just play it safe and go, look, I'm just going to belt and braces. I'm just going to put in my 10 microfarads, my 1 microfarads, and my 10 ends, and she'll be right. But there are some gains to be had here by months in something like this for volume. And then that might come down to here. Look, we've got 330 microfarads down here. You might have used 100 microfarad somewhere else. Could we have used, the 330s somewhere else where we used our 100 microfarads or whatever? For, a complex, as FPGAs are often complex, they have 5-6 different power supplies. That's not uncommon at all for a design like this. And, can you optimize the number of parts? Now, this isn't the best design for this, but talk about transistors, for example. If you're doing a lot of like switching in your design or whatever and things like that, well, you might be using like different types of transistors for different reasons. You might need, this one's slightly higher, I need more current for this one. Well, can you actually consolidate these parts? If you've got a high power transistor here that might cost 10 cents, and you've got another transistor which you don't need the high power, but it costs 8 cents, like, do you actually need to save that 2 cents and then have a whole extra reel and go and source it and take up space on your pick and place machine just because you didn't want to reuse this 1 amp transistor, for example, where you only needed 100 milliamps and you chose another transistor? Like, can you reuse parts like that? Diodes are another classic one, for example, where you might use a 1 amp diode on your input, for example, some sort of clamping or protection, reverse protection or something, and then you might need another diode in your design. Do you actually need that to be a 1N914 or some other, a signal? Can you actually reuse that same power diode? Try and consolidate your parts and reduce the number of line items on your BOM. Now, the third type of optimization, once again, it's another design for manufacturing technique. We have to go back to our pick and place machine, is consolidating footprints. Now, this one, actually, look, this one has, yeah, I think, look at these O201s. What a pain. Do you really need O201 capacitors? Look, these 1 microfarads. Do you really need 1 micro O201 footprints? That's ridiculous. That's half the size of an O402, which is already small. Do you really need that? Do you really even need to go to O402s? In this particular case, yeah, they probably do. But in a lot of cases, you can actually pay more to get boards assembled because they've got O402s. And it might also limit the number of manufacturers you could use, especially local manufacturers. For example, let's go back to this Yamaha machine over here. It's really expensive, like kind of like one of the top of the line jobbies. Yes, it can do O201, right? So, you might think, okay, I can use O201 resistors on my design. No. Don't. Look at the fine print, okay? Let's go over to here. They've got different types of heads. The ultra high speed head, for example, yeah, it can do O201 parts, but they physically have to change the head on the, or use a different head on the pick and place machine to actually do that. And the reason that these smaller parts can go faster is because they've got less mass. They can pick them up, zoom, all around the board. They can move them faster because then they won't fall off because of the mass of the parts just being held on the nozzle by a vacuum. And the heavier the part is, the slower the head has to move. You've got a giant big power resistor. It has to suck it up and then clunk, 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 move it over place. But an O201 goes, that's it, done. So this is where the multiple heads, and look at this, the flexible head here, for example, 0603. So if you do all of your design with 0603 footprints, they can use this flexible head, although there's lots of pick and place machines out there that will only go down, especially older ones, and the cheaper ones are used in some local manufacturer or something like that who's not really high end. They might be limited to 0603. They might be able to do 0402 for you, but there's actually going to be a lot of wastage. So your manufacturer might actually tell you, like, allow 5% or 10% for wastage, for example, especially on like smaller parts. And especially if you're using semiconductors, or chips, like real tiny little packages, they might actually be expensive little devices, or really high precision resistors, for example. You can pay $1 for a high precision, like a really good high precision low tempo resistor, for example. So like if you choose a real ultra tiny one and there's 5-10% wastage, that's going to add up to your assembly costs. So they might say, okay, we need 3,000 of these parts, but give us a reel of 4,000 because we're going to waste a lot of them. And there's a waste bin on the pick and place machine where all these fallen components just drop off and fall into. So this is why, if I was designing this and I looked at this BOM, I was doing my BOM consolidation, this one sticks out like a dog's hind leg. O201. Is it the only O201 part? Oh no, there's other one. Okay, so they're using some others, but it might stick out, sort by package type or whatever, and it might pop out. Oh look, we're using one O402 in this entire design. Really? Do we have to? Can't we just use an 0603, please? So just going that one part under a certain size could cost you, a lot of heartache and a lot of money as well as going one part over the number of reels that your assembler can actually support. That can add up to a lot of heartache and a lot of extra cost as well. And they often won't tell you this. They'll just happily accept your project and go, yes, we can assemble that, no worries. And they'll give you a quote and you won't even know that they're charging you more. So as I said, we won't get into the fourth one, which is BOM optimizing for cost. Although I've got a video which might come up. Let me know if you want to know. See a video on a 1 cent voltage regulator. Is it any good? I was going to play around with it and see if a 1 cent voltage regulator can actually do the business. Anyway, let me know. Give us a thumbs up if you want to see that. Leave it in the comments down below. But anyway, there's so many more ways that you can optimize values in designs like this. For example, like we've got an I2C line here that's going to have certain pull-ups, and the lower value pull-up for your I2C line, the higher speed because it's an open collector output, the higher the slew rate, the faster the slew rate, for example, and the more speed you can get out of your I2C bus. So if your confuser popped out the value of like 1.8K for your pull-up, well, do you need, and you don't use 1.8K anywhere else, well, why not use a 1.5K? Yeah, it might use a bit more power, for example, and that might be a trade-off that you have to go through your design. This is all part of engineering. Yeah, can I trade off the extra power for the 1.5K pull-up resistor, or even 1K pull-up resistor, versus the calculated 1.8K pull-up that I thought I could get away with? It might be worth it because you save an extra reel. And this video actually was originally going to be me just going through like a dozen different open source designs on the market and just looking at all values and actually going into the data sheets and trying to calculate, can we get away with certain values. LEDs are another classic example. Like you might calculate, okay, I want 10 milliamps to go through my LED. It's going to be like a pretty bright one. I want 10 milliamps in there. Well, and your confuser pops out the value, well, I need a 680 ohm resistor. Well, I don't know. Can you get away with, like, does it have to be that exact brightness? Can you get away with a little bit more, a little bit less to consolidate your BOM items? Anyway, let me know down below if you do want to see that video where I actually go through a bunch of designs and actually spend hours and hours actually looking at the data sheets, say for this, and figuring out, do we actually need that value? Do we need precisely this? But yeah, I decided just to show you well, in this case, 3 different ways to consolidate your BOM. And yeah, it's not applicable to all designs. You may never get to that stage where you need this, but hey, if you want to level up your skills in electronics design, then BOM consolidation can be a vital step in part of your design for manufacturing process. Just as an essential step in your design. You draw your schematic, you do your BOM consolidation, then you do your ERC, and then you lay out your board, and then you do your other design for manufacturing stuff, and it's all tied up in there, whichever order you want to do it. It can be really important. So anyway, hope you found that useful, and if you did, please give it a big thumbs up, and as always, comment down below, especially like what things have you opted on, what other things have you optimized in designs where, oh, look, it was marginal and I had to actually, seriously, it may pay you to actually spend like a day or two's engineering effort actually building up a prototype of this and testing it over temperature and stuff like that, just to verify that, the value you chose can actually work, even though it's, it might be slightly outside the margin, and you might try some tolerance resistors. You might even do some Monte Carlo simulation analysis, which is Monte Carlo analysis in simulation. Have I done a video on that? I think I might have. Try and find that. Is where you can test your design for different values, spread in your values, like 5%, 1% tolerance resistors. It'll, go plus minus 1% and rerun the simulation and tell you if it's not going to go tits up on you and things like that. Anyway, leave it in the... Go on for hours. Leave it in the comments down below of what stuff you've optimized. Have you really saved some, big cost or big heartache by doing the BOM optimization, or do you just never bother? Let us know. There's valid reasons for just, like in this particular case, they didn't bother. It's very clear. This is one of the, one of the most amazing examples I've seen. You can tell nobody's even bothered to BOM optimize this, and that might be fine. So nothing against the designers of this thing. There's valid reasons why you wouldn't bother. But if you're going to take this in a high volume production, I would not go into high volume production of this board with this BOM like this. I find it highly offensive. It's just, no. I would not, over my dead body, this thing's going into production with all these different, with like 76 minus 27. 49 different value resistors, 49 reels of resistors on this thing. Like, no, over my dead body, that's going into production. And I hope you feel the same way, because that's the engineering spirit. Catch you next time.